Hi, my name is Drouin-Touchette, and I'm a grad student at Rutgers University, and I'll present work today that done with my advisor, Piers Coleman, on self-consistent approach to local pairing in or multiorbital superconductors. Our motivation today is about the iron-based superconductors, which I present here, the general phase diagram, kind of schematic, with the large spin intensity wave sector, which I won't be touching about, but what's interesting is these very large superconducting domes as you dope away from the nominal valence of the iron atoms. You have these two large superconducting domes. And interestingly, as it was pointed out in 2018, if you look at the maximal value of the superconducting gap versus TC, it has a universal value of about 7.2, which is different from normal BCS phonon-based superconductors. And this is throughout the family of iron-based superconductors. And in spite of wide morphologies of Fermi surfaces. So in some cases, you have electron pockets only, electron and hole pockets and hole pockets. And these very different Fermi surfaces all have the same 2 gap over TC ratio. And this for us suggests a local origin of the pairing for these superconductors. And who says local physics for the outbase needs to talk about the Hund's metals or Hund's coupling. What does Hund's coupling do or wants to do is wants to maximize the total spin per site. So you can think of it as a ferromagnetic orbital-orbital interaction between the spins. And this led to the idea in 2011 by Ian Howland Kotliar of Hund's metals. So of strongly correlated yet itinerant multi-orbital systems. These are systems that are away from half filling, have very low coherence temperature, below which you have normal Fermi liquid T-square resistivity. And in that phase above this coherence temperature, large fluctuating moments in the paramagnetic phase. Which is seen in X-ray emission. And this leads to a lot of singular features that are seen both in experiments and in DMFT studies of these compounds. And what we've done is we've developed a quick and efficient method that obtains the essential Hund's metal feature, and in which now we can include pairing diagrams to see whether we can get superconductivity out of the Hund's pairing pair, out of the Hund's state. A toy model for this is the dope Hund impurity. The simplest model that we're considering is 2 sites, called orbital, really, in this case. So we're having a quantum impurity model with 2 orbitals. And we consider an Anderson impurity model where we can let the valence fluctuate between 0 and 1 being the half-filled impurity and site. And these spins are coupled ferromagnetically via Hund's coupling. And so each orbital here is either hole-filled or empty, or spin-unfilled or has a spin. And with the use of Splay fermions Ks and Schwinger bosons B, what we can do, we can then extend this SU2 spin symmetry to SUN, and this controllable larger limit allows us to unify the Auerbach treatment of quantum magnetism with the Parcolin-George Kondo effect approach, and we can treat those two on the same foothold together, on the same standing. And this is a very strong method, which boils down to having this hybridization vertex here. Between the conduction electrons over here, the Schwinger bosons and the holons, which then leads to only 2 self-energy corrections for the holons and the bosons at the large n limit, which we can then solve with the Dyson equation to extract thermodynamical and dynamical quantities. And this has a large, this is part of a large body of expanding body of work with work done on the 1D Kondo ferromagnetic chain and antiferromagnetic spin chain, a DMFT embedding, and our work on Hund Kondo impurity and doped Hund impurity. And in particular, I'd like to flash the results of the last one that we put on the archive last week, where we saw we were able to map the full phase diagram of this Hund-Anderson coupled impurity. What we can see is that for impurity close to half filling here, where I point my clicker, we have this large singular Hund phase. This is a phase with singular scaling of the spin susceptibility that looks power law scaling. And in that phase, we have a large emergent moment. As you can see here, I've got the impurity moment in pink. You have this jump to a large emergent moment. And if in the end, at very, very low temperature, an effective Kondo temperature that's much reduced compared to the bare Kondo temperature that you would have. And the question remains that this singular scaling here has been shown to be related to local spin fluctuation induced Cooper pairing. And so what our question is, out of the Hund state, can superconductivity rise? And for that, we need to include pairing diagrams between the conduction electrons. So the conduction electrons here would be paired if and only if the spin-ons here and the holons are themselves paired. So how would I have even spin-ons and holons paired locally? So the origin of spin-on pairing is actually quite simple. If we consider the 3t2g, the original iron atom scenario, the 3t2g orbitals, in the atomic limit, they share a common axis. Two of them always share a common axis. So the xz and yz always share the z-axis, and vice versa on three of them. And spin-orbit coupling can act together with Hund's coupling within the Hund's coupling manifold and leads to a orbitally selective easy plane anisotropy on Hund's coupling. Looks a little bit like this, where you have your normal Hund's coupling, and then some easy plane anisotropy on each of the bonds. And if we take that to its utmost limit, we can see that this is going to lead to some type of XXZ spin Hamiltonian between two orbitals. And one easy way to decouple this in the Schwinger boson picture is a triplet valence bond. So you can see here we have a triplet pair between orbitals 1 and 2, for example, that we've decoupled with a pairing field. And this, along with Hund's coupling, which acts as a force to delocalize the spin-ons and make them mobile around the multiorbital system, leads to a bosonic triplet resonating valence bond state, very much similar to the idea proposed by Coleman, Comigiani, and Koenig in 2020 on triplet resonating valence bond proposal for the iron-based superconductors. And the question here remains is, can we dynamically generate bulk TRVB superconductors with only this through a minimal model? And the step one for this is to, well, we have a pairing of a triplet pairing for the Schwinger boson due to this XXZ-like term in the Hund's coupling. And we can seed in an antisymmetric holon pairing. So that's what we're going to do at first. We're going to seed that in and see what happens at the end with the conduction electrons. And when we do that, here I show a measure of the Fermi liquid-like feature of this quantum impurity model, the conduction electron phase shift. In black here, you can see the conduction phase shift being close to 0 at high temperature. That's the paramagnetic phase. And then hitting 1 here, or pi, as a local Fermi liquid develops. This is in the absence of any Hund's coupling or any pairing delta. But as we increase Hund's coupling with no pairing whatsoever, we have a much reduced Kondo temperature over here, as I explained in the phase diagram. But then the curious thing is when we include this delta here, and we've seeded in the holon pairing, we have a complete destruction of this no-zero Fermi liquid, and the pairing of the holons here leads to a preformed triplet pair and the destruction of that Fermi liquid. And we can see this here with the on-site pairing of the conduction electrons. As these two anomalous propagators are non-zero, the final conduction electron propagator, anomalous propagator, will be non-zero itself. And we have this pairing term here with a spin symmetric, orbitally antisymmetric, of preformed conduction electron pair. And with an even parity pairing vertex in frequency space. And as we see this holon pairing, we can see this pairing vertex being non-zero. And if we allow DMFT-like self-consistency, and holon pairing will now lead to conduction electron pairing and vice versa, all promoted because of this XXZ Hund-like term. And so this is a kind of a work in progress, and this is going to be the subject of future work to embed this in a DMFT-like loop. But nevertheless, how can this solution here activate a Cooper logarithm, the spin symmetric orbitally antisymmetric preformed pair? If we put this on a simple square lattice, there's going to be no support on the Fermi surface. Because of the orbital nature of these pairs, there's going to be no support on the Fermi surface and no Cooper logarithm and no superconductivity. But however, if the center of symmetry of this lattice is off of the atomic site in a non-symmorphic lattice, the Cooper logarithm is activated and we have bulk superconductivity. And this is actually the case for the iron-based superconductors because of the puckering chalcogens and pnictogens. As you can see here, the center of symmetry is off and is between two sites. And this will lead in the end to an alternating gap structure between the sites and a bulk superconductor altogether. In conclusion, the Hund's coupled systems provide a fertile state for states for local Cooper pairings. And Hund's coupling along with spin-orbit coupling leads to a pre-paired interorbital triplet state instead of the local Fermi liquid. That's this green region over here. And when this mini TRVB that's formed over here can now hop around in the non-isomorphic lattice, we will have a fully gapped superconductor, which is work that we're now in progress and expanding there. And on that, thank you.